building up knowledge about software engineering using AI. Am I correct?
Yes.
Yeah, and also in software quality, so things like software defects, maintainability, and from a specification. And interestingly, one of your recent research is towards automated grading of UML class diagrams with machine learning, in which you described an exploratory study on the application of machine learning for the grading of UML class diagrams. It's especially interesting for me because one of my ongoing research is also about automatic grading of pseudocodes and programs in general, but not using black box static analysis techniques. It's also interesting to me about the use of machine learning in automated grading. So I would really love to talk to you more about it later. Also, Professor Shodrong's recent activities include organizer and chair at international workshop on analytics and mining of model repositories. And he obtained his PhD in 97 from Leiden University. Our students were not probably born yet during that time. Okay, that was my quick introduction of Professor Michel Chaudron. For our lecture today, the topic is software design principles, mainly in relation to software architectures. But before we proceed, I think it would be nice if you students can turn on your cameras for a while and say hello to our guest professor.
Oke, gimana turn on kamera dong?
Hello, good morning, everyone. Nice to see you. Oh yeah, it is actually nice to know that there. It is nice to know that there's people on the other end,
and
not just photos. Yeah, take a look at page 2 as well. But so there's around 40 people joining the meeting. Yeah, thanks everyone. Let's see if you think you have your challenge for bandwidth, feel free to switch it on. But for me, it's nice if I see a face occasionally, and I'll. Shall I take it from here?
Yes, please.
So I've also opened the chat window. So I will, if there's questions that I can answer during the lecture, I will answer. Otherwise, just try to send me an email, and then I'll do that. So I suppose that I need to now share screen. Yeah, that should be this one, I think. Are you getting that?
Yep.
Okay, wonderful. I have to enlarge this a little bit on my screen so I can actually see what's happening as well. So thank you for the kind introduction. Thank you for inviting me. Actually, I have visited ITB twice or 3 times by now. Last time was in 2016, I think. And then I actually gave a lecture while I was visiting. And COVID is now an opportunity that people start to teach online, and makes it a bit easier to do the teaching remotely for you people also. But of course, it would be much nicer to be there in person. So maybe in the future it happens again. But just to say, I'm not a total stranger to the ITB University. Currently, I work in Eindhoven in the Netherlands. Actually, I just returned this summer, and I've previously worked for 8 years in Gothenburg in Sweden. And prior to that, I was in Leiden and in Eindhoven. So for me, it's a bit of a return. So my topic of today is software architecture and software design principles. I will not touch so much on research topic. I've included one slide at the end a bit. But I'm teaching this course on software architecture design for quite some time, both in Eindhoven and in Sweden. And it's I've chosen to this topic. One is a bit of an introduction, and the other is a bit deeper. I understand your course is on service orientation, and I think that some of these topics are relevant. Whoop! I don't know. I don't know what happens on your screen, but in my screen it fills with something I don't want to see. There we go. Let's try to continue. So the course is called Software Architecture, but I want to emphasize that it's actually architecting. It's actually a verb, right? It's something that you must practice. And during this lecture, we don't have a lot of time to practice, but I do recommend that you practice it at home or with your teacher. So this is the outline of my lecture. I have an introduction of myself and of software architecture, and I'll motivate why software architecture is important. And I have a summary of the first part, and then the second part is about software design principles, and I have a summary of that part. So I imagine we can have 2 times 45 minutes with a small break. Satri, is that okay?
That's good.
Okay, then we move on. So this slide introduces me, but I already mentioned this. Indeed, my core area is in software architecture, software design. And recently I started looking at how to use artificial intelligence for making better software engineering tools. And that includes both machine learning, knowledge representation, and information retrieval. So the objective of this lecture is actually to teach you some knowledge, mostly concepts and terminology about software architecture, but then also knowing about some design principles. And there's a skill part to this, and as I said, you only learn it by doing. So I have a few questions in the lecture, so you can maybe try to participate. Yeah, again, so I use these slides, and one of the recommendations that I have for my students is architecture is also about thinking about your system at a conceptual level without worrying about the implementation technology, right? I want you to have an abstract picture, an abstract idea. Okay, which building blocks and which systems do I have? And then technology is always a way to realize it. You shouldn't mix up your technology and your conceptual idea. Personally, I like this topic of architecting because it combines many topics. I can see it's like the integration of many pieces. You need to understand a bit about different ideas, maybe databases. You need to understand the effect of distributed systems. You maybe need to understand complexity of algorithms. And an architect is a bit of a generalist in the software engineering team, and he knows a bit about everything. Often there are specialists that he works together with if it deals about details about security or details about performance. But then the architect knows how to bring everything together. I'm sharing an office space, so there might be some sounds in the background. So this is the books that I recommend. So these books are by some authors in the US, Len Bosbo Clemens and Rick Kessman. It's fairly practically oriented. They also apply their ideas in consulting with companies. The second book is a bit older, but it was one of the first books on software architecture. And it is a very nice starting point for reading more. And I think if you search, there's a technical report online that has exactly the same title and content as the book. So the other thing I would like to point out is that there are standards for doing software architecture. The old standard was called 1571. And there's a new standard, which is a revised version, with a completely different number, 42010. And both of them are actually about how to describe what is software architecture and how to describe it. So let's move into that topic. What is software architecture? Let me start with a definition. This is actually a definition from one of the UML books. An architecture is the set of significant decisions about the organization of a software system, the selection of the structural elements and the interfaces by which the system is composed, together with behavior specified by collaboration, but also the composition of these structural and behavior elements into larger system. And as part of the architecture, there's also an architecture style that guides how these parts work together, and surface orientation can be one of those styles. But the nice thing about architecture is that there's many definitions. And actually, in my class, I typically discuss a few. And some of these definitions, they highlight different aspects. So this is the second definition. It says the fundamental organization of a system embodied by its components, their relationship to each other and to the environment. Moreover, there's principles that guide the design and evolution. So what I like about this definition is it says now architecture doesn't exist in isolation. It exists in an environment and exists in space and time. So you can only assess whether your architecture is good if you understand that it's a good fit in the environment, right? It needs to provide the good functionality and the good performance and the good security. So, and those criteria, they come from the environment. Moreover, it says that there is an evolution of architecture, and I'll come back to this later. Software systems, they tend to evolve. This is like a law of nature. We haven't seen any software system that doesn't evolve. But if it evolves, then somehow there must be a plan on how to make it evolve, how to adapt it to changes, right? And for that, you need principles guiding the design. So it's not only enough to create one picture that defines the structure of an architecture. You need to define, okay, if we're going to have a change of this type, then we're going to handle it in this and this manner. Right, let me motivate a bit the importance of architecture. I start with a citation from a gentleman from a telecommunications company that a correct architecture has the single largest impact on cost and quality of the product. So at least that is evidence, but let's see if we can understand why this is the case. Here are some examples of systems that contain software nowadays. You see an ATM machine, I see a satellite, an airplane, it's something like a tablet. There's a complicated medical machine, and of course there's browsers and search engines. All of them contain software, and not a little nowadays. And most of these contain a lot of software. In these graphs, I show how software grows, underlining that actually there is always evolution taking place. On the vertical axis, you can see the size. In this case, it's a logarithmic scale. And this is the size of software in airplanes. If you know airplanes, you recognize the types maybe. But if this is a straight line on a logarithmic scale, it means there's an exponential growth of software in airplanes. And the impact of that is really profound. And many companies don't really understand that if they start building software, their software might grow exponentially. Because if you have 10 developers this year, you might need 100 developers in the next round, right? Because you have an exponential growth of software. And I've taken other examples, and the left shows complexity of operating systems, and this is software in TVs. And we see exactly the same trend. There is going to be an exponential growth in software. And one more illustration of this is graphically. I have some picture that shows the design. This was the design. Let's call it the architecture of a small computer game, and it has 5 components. After 6 months, they made a second release of this software, and it had now 8 components. And again, 6 months later, another release, and now it has 16 components. And you start seeing the complexity increase. And another 6 to 9 months later, the next release. Okay, so at the start you think, okay, I know my software, I can handle this. But after 2 years, you end up with a large number of components and a huge number of dependencies. So this is where we need architecture for. We need to ensure we need a tool for handling this complexity. And I'll use a metaphor later. We need to divide rooms in the house so that we can limit changes to one room, or we need to design the garden that we have certain plants in one corner of the garden and not in the other parts. Otherwise, it grows into a jungle. Although I like jungles, they're beautiful, but not for my software. So I hope that you understand the significance of growth of software and the need for managing this growth. I think this is the last slide on growth. Complexity actually comes from different angles towards us. If you look at modern software, it's 1 to 25 million lines. Uses 2 to 10 programming languages. Uses some 100 libraries, up to 1,000 programmers, maybe millions of users if it's web-based software, and it might live for 20 years, right? So it has many parts, and you can see the colorful parts at the top, but we need to organize those parts. And people in space, they tend to think that they make complex systems, but their rocket only has 2.5 million parts. So this is peanuts if you compare it to 25 million lines of software, right? So we need to boast a bit more about the wonderful engineering that the software engineers can do. Right, more different angle. So why is architecture important? Typically, architecture decisions are made mostly at the start of a project, but not only, mostly at the start. And they're typically the decisions that are important because they affect cost, they affect risks, and they affect the quality properties of the system. At the same time, those are typically the decisions that are difficult to change later in the project. But those important decisions, they determine 90% of the cost and the risk of a project, right? And you make those decisions typically in the first 10%. So you want to get those right. At the same time, it's not the case that once you make them, it's fixed. And this is also the difficulty. You will continue to run into decisions that you need to add. And sometimes you need to revise these decisions. And it's if you're in system engineering, then the hardware people say, okay, now we can't change this anymore. And the software people will always say, oh, we can change it. But this is a risk as well. I'll go over this a bit quickly. So what does architecture help you with as a business? It helps you to reduce time to market. It helps you be able to integrate, for example, existing components into your system. Also reduce development costs. I hope I've argued already that it helps you reduce the maintenance costs because it helps you avoid the spaghetti and the jungle of complex system, and it helps you improve product quality. And yet there's still another way, and there's still different ways of understanding this notion of architecture. And I've been studying in many companies why architecture is useful, and I think one of the key things of why it is useful is it's a means of communication. It's a means of understanding together as a team the same thing by making a graphical representation. Do we see which component exists and how they relate and who's responsible? So that's understanding, and it also relates to understanding of the context. Then it describes, okay, I think this is what our system looks like, and we can use that for reasoning. You can say, okay, which are the main functions that it has and how our functions group together, And then there's also guiding. Say, okay, if we agree on this design, yeah, then this team should make this functionality and that team should make this functionality. So it's also a guidance for the design, but it's good to realize that there's these different functions of architecture. Yeah, and I tend to collect architectures in the wild, mostly from companies, sometimes from open source projects. Not all companies are eager to share their design, but you can find some examples online if you search well. Yeah, so you run into a variety of diagrams. This is called the e-commerce architecture blueprint. Okay, so you can, I would say, in the wild you run into a huge variety, and not everything would pass the academic exam for architecture. But don't forget there's different purposes, right? This diagram clearly shows some type of layering. It shows grouping. It suggests that there are some databases, right? They use this cylinder shape. And then, okay, if you see this diagram, you can reflect a bit. Okay, I've told you that architectures are for understanding, they're for describing, and they're for guiding. And this example, I would say, is mostly for understanding and maybe for communicating, right? It doesn't offer all the details for guiding, but that's okay. You can still find it useful. I want to continue with more examples. Okay, so here's an example that has a bunch of boxes, and they're also nested actually. And there's a few matchstick men appearing on the left, representing users. And here one of the key elements of this is to show a decomposition. The other thing that is nice about this is that it's a standard notation. Actually, it uses the UML notation, and I hope some of you have seen it, this notation, so you can read it a little bit. One of the things to understand from architecture is that the description uses this perspective of viewpoints, and it's a bit like viewpoints for understanding a house. Right, there might be one house that describes the structure of the walls. There might be one that describes the electrical plan. There might be one that describes the plumbing or the floor plan, and those are different models, different representations of the same thing, but they focus on one specific thing, right? And this is a benefit, right? Because if you do everything in one diagram, it would get complex, become more difficult to reason about. It would be difficult to maintain. So there's also I'll come back to this later. There's a separation of concerns in how you represent your system, and the terminology for understanding. Okay, we look from the system from a particular viewpoint, and then we see one part, which is called a view. But in software engineering, we mostly use this 4+1 views model. It often shows users and use cases. And then it shows a structure, which can be class or component or package, and their dependencies. That's a static perspective. Then there's a behavior perspective, a behavior view, and you can illustrate your behavior of your system with sequence diagrams or activity diagrams or workflows. And then there's a third one that's important, and that's the deployment view. And this shows where these components, you can see their names are actually reappearing, where these components are running in a physical network. And it might be in a distributed system nowadays, most often, right? It could be running on your telephone. According to this approach, there's also a fourth view, which is called development view. And that says, okay, how do we organize files for the developers? Which file represent which class? How do we apply version management? And of course, it can be linked to the structure of your design. I don't want to spend a huge amount of time on this. So if there's questions, can get back to me later. The idea being is that these different views actually they correspond to different questions as well. So for answering one question, you can look at one of these views. So in the center, the use case view, you can say, okay, if I want to know what the system does, where do I start? You start with the use case view. If I want to understand the structure of the system, you go to the structure view. If you want to understand the behavior, you look at the process view. And for some questions, you actually might need to combine, right? So if I want to say, how does the system perform? You might need to understand both the behavior view and the deployment view. And that's fine. Yeah. The other thing I would like to clarify is that if you go into industry and people, actually many people like to call themselves architects, but then it's good to ask them what type of architect, because there appears to be many types of architects around. You can be the architect of an application and you talk about classes and packages and components, and you can also be the architect of a system, and then suddenly you're not only worried about the software, but also about the system as a whole. So imagine this is you're building an ATM or an airplane, and software is part of it, but you're actually designing the system as a whole, and that is your scope. And then there's also something called enterprise architecture. And I have a separate slide on that. Enterprise architects, they have their own, you could say, terminology, their own view on layers, and their own view on how to describe a system. And they like to start indeed with business level concepts, business processes, business goals, and then they translate that step by step into a technology, that IT technology that supports these business processes, which supports the goals. And here you see a typical example for that type of layering, starting with business values and innovations, going to enterprise capabilities, maybe the knowledge, people and processes, and at the technical level, it's the technology that supports the entire organization. Yeah, the other thing that you find if you search for architecture is you get pictures like this. And I suppose this is the fact that no one can control the way that language is used, but this is from an architect's perspective, this is the network topology, and it's not the architecture from a software architecture perspective. So please try to understand this difference. Right. So I mentioned some business objectives. You can also have benefits of architecture for the development. And I mentioned already the development is dealing with complexity. It helps you to answer questions like, okay, what happens if this function needs to be added? Or what happens if we change this library? Or should we have another layer? Right? And those are what if questions. And by having a representation of your architecture, it helps you reason about and decide about this. It can also be used for feasibility and risk analysis, because based on your architecture, you can reason what would be the performance, or is it possible to build an algorithm that does something so fast, or do I have enough storage capacity, right? So those are technical analysis possibilities. And of course, in the end, it's also used for estimation and planning. If I have 10 components, then I can say, okay, and I need one developer for every component, and this component would take so many months, another component would take so many months, and I allocate the development of different components to different teams, and I use it for planning and progress monitoring. And here's a few examples. This is, let's say this is an architecture. And we're a bit suspicious about this green box, to say, well, if we look at this from a complexity perspective, we can see there's many other components connected to this. And maybe we say, maybe it's a bit too much. Maybe we can simplify it by breaking this up and breaking it down into smaller units so that we have fewer connections and make it easier to develop and easier to test. Here's an example of using the architecture diagram for an what if. What if we change this component which is in the orange box? Now then we need to check. We need to check everything that interacts with it, whether the change propagates. And then we find, it works with these components. So we need to check whether our change affects these components. And then I mentioned that software architecture determines quality, and quality is very important. And there's two types of qualities. There's the quality of the system that's observable during execution. And those are quality properties like performance, security, availability, functionality, and usability. And then there's also properties that are witnessed that you can experience in the development process, right? And they say that those are properties like modifiability. Is it easy to change? Portability. Can I use my software on a different technology platform? Reusability, integratability, and testability. So these affect how fast can I develop it, or how costly is it to develop it? How easy is it to change? And this is why architecture is difficult, but also interesting, I think, is that the architect needs to bring all of this together. He has to think about all of these quality objectives, and he has to have knowledge about, okay, these are my technical possibilities. And he comes up with, okay, if I design it like this, yeah, then it satisfies, so I need to polish a bit here, or I need to apply a specific strategy or design pattern over there. So that is, I think, the beauty and the art of architecting. So I move into the summary of my part 1. So software architecture is a critical aspect in the design and development of software and systems, because nowadays most systems are very software intensive. We discussed some definitions and objectives of software architecture. And in particular, we discussed the relation between software architecture and quality. And my quotes at the top again, do practice. Don't expect that you can start leaving university as an architect. It's really necessary that you practice on designing systems and architecting. And interestingly, there are not so many books that describe cases. I'm trying to write some down that I use as assignments for my students, but there's always a balance between it shouldn't be too simple, because then you don't have the realism of actual architecting problem, but it should be doable as a student project. So it's not easy either. So this is a good opportunity to ask questions about the first part.
Okay, students, do you have questions?
You can try the chat.
Don't be shy.
Huh?
Don't be shy, students.
It's okay. I won't bite.
Okay.
Okay, then we just continue, I think.
Please go ahead.
Hello.
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 Okay, sorry. So hello, Mr. Michel. My name is Yoel.
Hello.
Just now we discussed about the aspect of um, software architecture, that it
Mm-hmm.
always evolves into something because
Mm-hmm.
into something else, because probably um, we have a need that doesn't exist in the past, and then we have another need or a new need that we need to accommodate, and then we
Mm-hmm.
change the architecture as it evolves. So my question is, when we architect a software, probably we don't always envision that it's gonna evolve so big, or we don't probably think that it's going to be the next big thing. So we don't expect 10 million people to suddenly use it.
Mm-hmm.
But somehow it grows into, yeah, probably the software is being used now by 10 million people. And then we thought
Mm-hmm.
that, okay, now the architecture is no longer be able to support the software needs.
Mm-hmm.
So is the re-architecturing of a software an inevitable thing? Because I think I also read somewhere that when we build a software, sometimes we don't want to over engineer the things. So
Mm-hmm.
sometimes we need it just to be simple, but
Mm-hmm.
then sometimes we also would like to make it bulletproof so that it
Mm-hmm.
can stand the test of time. So
Yeah.
yeah, I think my question is, when where do we balance things? For
Yeah.
example, if we go too simple, and then we might need to re-architect or
Yeah.
rebuild the software as a whole
Yeah.
very soon. But if we go into the other extreme, then
Mhm.
we probably will be building something very hardly, but probably it
Yeah.
won't evolve into what we have envisioned.
Yeah.
Yeah.
So this is a typical question actually. I remember when I lectured in Indonesia, I actually got a similar question. What I find is that students they work in startups and they say, we shouldn't over engineer, and I completely agree with that. At the same time, the pictures that I shown, they illustrate that things do get messy if you don't manage complexity. In IT, there's many technological helps, right? So in the last 10 years, we've moved storage into the cloud. Yeah, that saves you from worrying about many architectural concerns, right? It saves you from worrying about scalability, availability, and maybe also about performance a little bit. So that already is a way of reducing your architecture worries. Um, but and it depends a bit on your context as well. I have an anecdote from a telecommunications company, and they say we built an architecture for 4 years, and then we find that during those 4 years we built such a complex system that after 4 years we throw everything away and we start from scratch. And they say that there's two reasons. One is we've built a construction that has become too complex, and at the same time technology has progressed, and now there's better solutions because we've built something ourselves, but now there's some company that offers a package or a library or a framework that does something for us, right? That we don't need to build it ourselves anymore. And it's actually a topic that I would be interested in studying a bit more fundamentally, because maybe I'm getting a bit older, but I mean, when I started studying, there was no off-the-shelf database, right? You had to program your own data structures. Nowadays, we throw everything into a database. If it's either SQL or non-SQL, you don't think about it anymore. But it's a facility that you can now use that wasn't available. Okay, same for user interfaces. I don't know how many of you still make HTML, but I don't think very many, right? So in the 1990s, 2000s, we taught students HTML, but now it's become much easier for you to design user interfaces with all of the technology that's available. So if you start with one technology, I can guarantee you that after 5 to 10 years, it will look completely different, and you will need to migrate. Right? There will be a need, and then you better have an organized systems that allows you to do the migration in a manageable way, rather than have a spaghetti and you don't know where to start. I hope that's a bit of an answer to your question.
Okay, thank you, Mr. Michel. So I think the answer is more like probably rebuilding software is inevitable because
Mm-hmm,
technologies always evolves, and
mm-hmm,
therefore something new probably can cater to our needs later on.
mm-hmm,
But
mm-hmm,
what we need to prepare is how do we architect our things so that it can support us, maybe according to our need, maybe short term, mid term, or long term, and also
mm-hmm,
prepare to uh, also prepare about how we need to do migration if
mm-hmm.
the time has come.
Yeah,
All right.
yeah, I
Thank
would
you very
agree.
much.
And well, I can share another anecdotes as well. What if software becomes complex? So when I worked in Sweden, we had a neighboring company. Actually, we had two in Göteborg. Two main companies. One is Ericsson in telecommunications, one in Volvo. And Ericsson, they have systems where they have more than 1,000 developers working on the software of the system. And there's a huge amount of components, a huge amount of connections between them. And what they start seeing is, okay, there's now so many connections. The architecture has become so complicated that we have a slowdown of our productivity. We need to ask so many questions to understand how it works before we can add something that it's slowing us down. Yeah, so at some point you do see an effect on the velocity of development if your system becomes too complicated. And that's not just technology evolution, that's also functionality evolution. Right? And again, this is different. This is not the same for all the domains, right? But I would be surprised if you don't run into it. Yeah. And
Alright,
the
thank you,
other
Mr.
discussion it relates to is, of course, yeah, we want to develop agile, right? And then we don't want to have over engineer, but actually, if you read the agile principles, all of them are impossible to disagree with, because none of them are actually very strict guidelines. They say, we prefer working software over documentation. Yeah, everyone does. But no, in practice, they say, okay, let's forget about documentation. But that's not what it said. It's also not what is useful, right? You need to balance. You need to balance it. Yeah.
Okay, that was a great discussion, and it's also something so real that happened to so many, uh, you know, services that we encounter in our daily life, such as Dropbox, Facebook, etc. They started small, and then they have to
Yeah.
rebuild everything in another technology.
Yeah. The other example, I don't know if you know, is the Nokia telephones.
Yeah.
They were too slow in moving to a new technology,
Yes.
and
Exactly.
now they're dead. So almost.
Almost.
Yeah. So yeah.
Okay. Any other questions, students?
No. Shall I try to continue?
Oh, there's one question from the
Yeah.
chat. Hello, Mr. Shendrong. I'm wondering whether software architects actually do use UML diagram when designing or communicating with people with different roles from BMO.
That's easy for me to answer. The answer is yes. It's also interesting because I get this question from students also every year. Doesn't matter where I teach this course. The answer is yes. Actually, I've made a bit of a study of this more in depth than most people. I collected, for example, from GitHub in open source, how much UML is used. And there we have we found around 80,000 designs in GitHub. So that's the largest collection of UML designs in the universe that we have currently. And I've also done interviews with companies. And what we see there is, of course, it's contextual, right? Small teams making small products, they don't have such a high need for using UML. Larger organizations with many teams and long-lived projects and complex systems, they do have a need for systematic documentation, right? And also for graphic representation of their system. Then you can say, okay, I just use a box and lines notation. But what we find is that if you have 1,000 people in your team, or even 100, you can count on people coming and going in your team, and that's a fact of life. And then it's much more practical to have a standardized notation where people that come from the university, okay, I know this notation, I know what this box means, I know what this arrow means, and they can understand the diagrams much more quickly and more unambiguously than non-standardized notations. And the last comment is UML the best? I think it doesn't matter so much. You can think of alternatives and they will have the same advantages and drawbacks as any graphical notation.
Exactly. So, in maybe die-hard agile proponents, they usually say that diagrams should only be used to communicate, and you don't need to have a very formal rules of how diagrams should be. What do you think about that?
Yeah. So first of all, I think we shouldn't have diehards. I think people should be more flexible in life. Again, I mean, there's no evidence that using diagrams slows you down or makes you worse or anything. If there only exists positive evidence about the use of diagramming. Of course, you can do too much of a good thing, right? But that's not a problem of the notation. That's a problem of how you use it. So actually, we have run a survey in agile projects, and we've asked them, "Are you happy with your documentation?" And 60 to 70% of the projects say, "No, we would have preferred more documentation than we're doing."
Okay. That was good to know.
Yeah.
So that what we learn in school is not useless.
No,
Okay.
absolutely not. And I would also say that it's not. I hear this argument from, do people in industry do something? Well, I can assure you that there's lots of people in industry that do very stupid things. Yeah, so there's actually, you learn lots of good stuff at university, which you should bring into industry, right? And you have to convince them that sometimes it's a good thing.
Okay, thank you. Is that enough for Bimo? I think so. He replied thank you in the chat section.
Yeah,
We probably should move on to the next part.
yeah.
Or is there any other question? I don't think so. We can go to part 2.
Yeah. So I found recently I found a different metaphor for explaining this organic growth of software, because I think it is organic growth. So I have the picture of the computer game on the top left, and in my view, it has grown like this garden, which is beautiful but completely unstructured, right? If you ask where do I find my vegetable, there's no way you know where to look, right? There's no and it's not useful for evolution. So instead, I think you need to think of architecture as a design for your vegetable garden, right? And I've added this picture on the right here, because you have to imagine that in every box there will be a team of developers making the lettuce or making the spinach, right? And you don't want that to be mixed. You want the team to be able to develop autonomously. You also see that the picture on the left is not UML, but it is a useful illustration, right? But it does use boxes, and you see it just outlines the plan, and that's the essence of the architecture. It outlines the plan, and people know how to stick to the plan, right? So that people work in the same way, that they can understand what other components can offer them. Right? You can say, okay, if I work, okay, this doesn't work well for vegetables, but if one component works together with another component, okay, we know that we can expect this component to do something according to an interface. But this is currently my favorite metaphor for software development and architecture. And the topic I will pick up a bit more on is this notion of modularity. Right, so modularity means we have decomposed a system in parts, and those parts are ideally independent or largely independent, and we can understand them in isolation, but the system needs to be understood as the composition of the parts. So here's another example of modularity. It's a chest, right? Chest of drawers on the top. You could argue it's modular because there's different parts, but I would argue it's not stable, right? If you take away one drawer, then your chest will fall down and it breaks down. So you can think a bit about why this happens and what's the analogy with software and software architecture. Of course, on the bottom, I have a chest of drawers that doesn't have the same problem. Why is that? Because there's no dependency from one module on another module, right? I can change one module and I can change its contents, and it doesn't affect the other. Yeah, so this notion of dependency plays a role. You can have modules, but they must be independent in a way. Yeah, so this is the first design principle. It's a very generic design principle, right? It's decomposition. We want to break a large system into parts and make them independent as much as possible. Moreover, when we have a component or a subsystem, we want to be able to assign a single responsibility to that component. And this is something I will illustrate a bit more. So we can call this principle, we can call it decomposition, sometimes called divide and conquer. You can apply it hierarchically, right? You can have a big system and break it down in smaller functions. Yeah, and when we work in software, we have actually two dimensions in which we talk about decomposition, but conceptually they're different, and it's a bit difficult for bachelor students maybe. But I hope you're willing to spend a little bit of time maybe after the lecture to reflect on it. The first direction is a functional direction, and this is an example from a self-driving car. What do we need? We need a steering system, we need a braking system, we need comfort. Okay, this is seat heating, which people in Sweden have. I imagine Indonesia doesn't have so much of that. There's driving assist, so for example, lane keeping or automatic parking. These are functions of the system, and you can say, okay, I can make this part and I put it together with the other parts. But there's also a dimension which I call an implementation dimension. You don't actually change or add functionality. You don't break the functionality in different parts, but you stack pieces of a solution. So for a braking system, we will have device drivers that actually handle the sensors and steer the actual brake. And on top of that, there will be a controller that says, okay, I know when to do the braking and when to do the steering. And on top of that might be a user interface, right? And that's an implementation level decomposition. And it's not the same as a functional decomposition. So try to not, my message is try not to mix those up whenever you make a design. Yeah, so layering is a principle of design, and it is very valuable. It's also ubiquitous. It exists in almost all software systems that we make. And the idea is that you break it down in layers, and one layer can depend on the layer below it, but ideally shouldn't depend on the layer below that, because layers provide a insulation against whatever happens below it. Right? You don't want to be affected by changes below the layer that you're using. So you try to not depend on them. So I have some slides that illustrate an example. Actually, this is an autonomous lawnmower. I was a bit surprised, but I found a paper that describes this as a scientific paper. So I said I used to live in Sweden, and there people have a lot of space and they have large gardens, and I suppose they're lazy. Oh no, they're they're so large that that they need a robot for mowing the lawn. Maybe they're busy. Let's say they're busy. They need a robot for mowing their lawn. And we use this as an example for doing system decomposition. So here's an example. So we have at the top an autonomous mowing system. What are the functions that it would do? Well, it would have a mowing function. It would have a monitor my surrounding function. It would have a navigate function. It would have a monitor my health, for example, my battery, and it would have a communicate with the user function, right? And just so I recommend this as a first step in the design. Just break the function down in sub-functions. You don't need to show how they interact with each other. I don't want you to show down how they're implemented. So I don't need power at this part, because that's an implementation decomposition actually, right? So we don't need that at this point. And then you can make in the next step you can make a design, and you can say, okay, this is how I imagine that these subsystems would actually work together. And if you want, you can apply this hierarchically. You can break down systems into subsystems and have a hierarchical decomposition. I don't want to explain the particular details of this case. You can read it later. But again, if you have done this, I want to emphasize that the system decomposition is a functional decomposition. You break down functions. which is different from an implementation decomposition. You can again, I ask you to think about this later. Here's another example, and maybe here I'll give you a little bit more time to think yourself. I hope you recognize this type of a device. Nowadays, everything is of course part of your telephone, but in the olden days, there used to be devices like this. It's just a radio alarm clock. So it would have you could read the time and you could actually tune it to the radio, and then you could trigger it to start if you want to wake up, and then it would start playing your favorite radio channel. Of course, you can connect those to internet nowadays, and you can stream Spotify to wake up, but that's the idea. So just take a few seconds to say, okay, what are the subsystems in terms of sub-functions that would be needed? There would be a good decomposition for this this system. I'll give you 30 seconds, 1 minute, something like that. How's it going? You have an idea? I take that as a yes. I'll move on because otherwise I remain waiting. But I hope you've thought a bit about, okay, what could be components of this system? And maybe you've scribbled something on your paper, either as text or as a diagram.
Anyone? No?
Oh.
Okay.
I'm ready to show you my example. But you can check it against your own example. So I followed the same philosophy of trying to break down the system. I think, okay, I have a radio subsystem, I have a clock subsystem, I have a timer which knows when to trigger the alarm, right? And then I have some buttons for actually entering input. I have a display, and I have a speaker for actually generating the sound, the audio. And I asked you, so we should think of a single responsibility, and this is actually useful for various reasons. It helps you to understand, okay, what's the scope of what the system should do, but it's also good actually for coming up with the name of a component and maybe the name of the methods or the APIs that it implements. So I've made this exercise of, okay, what if I were to name the responsibility in a generic way, what would it look like? So I have the same components, but I reordered them a bit in time. So the radio is actually the audio supplier. It produces the audio data, audio signal that I need. And the clock is actually the time supplier. And the timer is the alarm time supplier. And the speaker is the audio rendering. And the input, okay, that's not a very good name, maybe input handler, and then output, visual output handler. You have to be a bit careful with names like handler and manager and controller because they appear all over the place. But you cannot just call it controller. It must be control something, right? Or handle something. But I just want to say that, okay, we can, and in software engineering and in computer science, we have to be good at this. We have to be good at generalizing, because what if I don't want a radio, but audio, say an internet stream, right? If I had called my component only radio, then I would have to think, okay, well, now I have an internet stream, where does it go? But if I call it audio supplier, then I know, okay, it goes in the same box because it's the same functionality, right? So yeah, that's how generality or generalization can help, and thinking about responsibilities can help you in the design. So the next topic that I want to talk about is dependencies, and in diagrams we often show it as an arrow. In this case, there's a component or subsystem A that depends on the component B, And it can mean two things. It can mean component A requires component B in order for A to work. And that's a typical functional coupling, right? A has a task. It asks B to do some part of the task and then gets the result, and then A continues. But there can also be dependencies that manifest themselves at the development time. For example, if there's a change in component B, then we know that maybe A needs to be checked whether there's an impact on A, right? So then it's an implementation coupling. Whenever B changes, we need to test B, but we also need to test A because the change in B might have an effect on A. So that's an effect of dependency in development time. And these dependencies, yeah, they arise in different ways. If A does a call on B, or if A has a method that references B, if A has an attribute that refers to B. Also, inheritance is a dependency. Then there may be other things that cause dependencies, and it's not exhaustive. And I think there's also this. I need to warn you that there's this dependencies that you cannot see directly in the source code, and they arise a bit more often in event-driven systems or Blackboard systems. You don't see the dependency in the code, but there's a implied dependency because they share data or they share events, or they both of them monitor something, and then one of them accidentally blocks or triggers the other while it wasn't meant to be. So there can be implicit dependencies. There can also be dependencies on the nature of the data. For example, maybe A assumes that when that it gets data from B and that B has sorted this data. Yeah, if you are developing your system, you don't need to express this dependency, but if someone else then changes something, then suddenly this dependency might be violated. Okay, another design principle is that if you have these dependencies, then they should point in the direction of stability. What does it mean? If we have A depending on B, then we want changes in B to be less likely than changes in A. And the whole point of having this is actually limit the domino effect of changes. Because you can imagine that you have this in layers, and then, okay, if I have a lot of changes all the time, then I get a lot of domino effect, and I need to change everything all the time. So if there's components that are at the bottom, that means there are many software depend on it. You want your basis to be stable, right? And we do the same for housing. Okay, now that we have introduced this notion of dependency, we can actually look at, okay, how does it affect the way that components relate to each other? And there's the notion called coupling, and it says, okay, coupling is the degree of interdependence, so the amount of dependencies between modules or components. So on the right, you see there's 4 components with only one arrow representing a dependency. So that's low coupling, which we say is good. And then on the left, there's many dependencies between all of the components, and we say, okay, this is bad. We don't want that. And you can justify this again by thinking about evolution and change, about retesting. Okay, which one is the more complicated? Which one is the more easier to evolve? It's the one on the right. And which is one easier to extend? It's the one on the right. I have another example of something that I think went wrong. Here's an example of 25 modules. How do they manage to have so many dependencies with only 25 modules? Something must have gone wrong, I think. And this is another angle where diagrams actually help you. If you look at the source code only, I'm not sure if you would get this overview of all the dependencies that you have built in. So again, I've argued already several times, why is low coupling or low dependency good? Modules are easy to replace. They're easier to understand. Often they're easier to reuse because they have more information hiding, which we'll come back to later. And often in runtime, we will see that there's less propagation of errors and failures. if there's lower coupling. So the counterpart, I'd say the other side of the coin for coupling is called cohesion. And cohesion is about the relatedness of functionalities or subsystem within a component. Right, so on the left you see a subsystem and it has 4 parts, but those 4 parts, they depend on each other, they're connected. That means that they do something together. There's a reason why they're together. Together they perform the same function, or they build on each other, or they. And on the right there's some components, and they just accidentally in the same component. It's not necessarily that they do anything together. So there's no cohesion. And for that reason, there's actually no reason for them to be together, right? Again, it makes it more difficult to understand, maybe more difficult to evolve. So we move on. So let's look at cohesion, and this is an exercise you can try to do yourself again. So I have my radio alarm clock. Maybe I changed the layout a bit, and I've written down the responsibilities below it. And based on this, we should be able to allocate new functionality because it's cohesive with the existing functionality. Where does changing the volume go? I would say it goes into the speaker because that's a rendering property. With changing the channel, where does this go? Where does this go? Which component should it go into? Yeah, I would say it goes into the radio because that's the source of the audio signal. Where does setting the date go? I didn't mention there was a date. I only talked about time. But then I hope that date is related to time. It's cohesive, so therefore it goes into the clock. Right? And that's where we should put the set. Now something we didn't think of at all. I would set the time zone. Okay, it's a time-related thing. So again, it goes into the clock. So this is currently my explanation for cohesiveness, right? And I very much welcome more examples. If you think of nice examples, please share them with me because there's not so many textbooks that have very good examples. Okay, summary. Actually, the advice on design is to go for high cohesion, put things together that belong together, and low coupling is the dependencies between modules should be small. So this is bad because there's high cohesion and high coupling. We don't want high coupling. We don't mind the high cohesion. Here we have high coupling and low cohesion. You can see that there's modules where the inner boxes are not actually related to each other, right? So we don't want that. Moreover, coupling is on the high side. Here we have low coupling and low cohesion. So you can see that there's the inner boxes have very little connections to each other. And this is low coupling. That means there are few dependencies between the outer boxes, but there's high cohesion. The boxes inside, they belong together. They do something together. Right? So this is the green box indicates this is the type of design that you want to go for. So okay, what are the tools that we have at our disposal for achieving a lower coupling? And one of the important principles there is called information hiding. And information hiding, the objective is to localize change, because what you hide is details that you have internal to a component, and other components that make use of it, they don't know about the details. They don't need to know. And because they don't need to know, it's possible to change it, right? So I do have the example of the woman giving the present to the girl. He said there's something inside. They implement the give present interface, and we can change what's inside. It's hidden, but we can still implement the give present method. So maybe I have more examples later. Yeah, so it's about avoiding information hiding. Is about avoiding dependencies. And it actually can be traced to a professor and a researcher in software engineering called David Parnas. I think he was Canadian. And he actually said, okay, you can make these difficult design decisions as the starting point of your design. So when you get the requirements, you say, okay, what could possibly change about my technology, or change which key design decisions could be different. For example, if I do route planning, I do a route planner from A to B. Yeah, what's typically going to change is the algorithm, right? Maybe we have a better algorithm. So the interface would only say, give me a route from A to B. And then we can change however we do this. If we can come up with a smarter algorithm, we can change it, and the users of that component would not be affected. Yeah. By the way, this gentleman who actually worked in industry quite a bit, he actually said, okay, do not only worry about the technology, but pay more attention to the fundamental ideas. This is a balance that we as educators, as university, often have to make. The students want to learn a lot that can make them productive when they leave university and start their job. Yeah, but we know that five years from now, the programming languages will be different, and the technology will be different. So that's why we try to teach you the principles as well as technology as a vehicle for understanding the principles. Yeah. Another angle on information hiding is, okay, that we have a component and it does some algorithm, some functionality. We also don't want other components that use this to try to look inside. And they can do this by using a method that's not supposed to be public, or by accessing data that's not supposed to be accessed. Right? So because all of those are ways of having dependencies that we want to avoid. So information hiding, it also has it also has a meaning of don't enter. Try to only use the interface for accessing the functionality. Oh, yeah, this is actually one of my other examples. How can you then come up with good design is by thinking about what does my component do, and that's often a responsibility. You can think about responsibility rather than how does it do it. And I think I was maybe telling my children a story or something about these three little pigs that make a house. I don't know if you know this story. I think it's a Walt Disney cartoon, a fairy tale. And the three little pigs make a house, and the wolf tries to capture them, right? And the first builds the house from straw and it's not strong enough, and the second builds it from sticks and it's not strong enough, and the third builds it from stone, and that's strong enough. So each of those pigs has a build house interface, but they implement it in different ways, right? One can build it from straw and the other can build it from stone, and we can change the internals of the build house components, but we keep the interface the same, right? Apparently it's a detail that doesn't matter, so we can change the evolution, and that supports evolution. It supports extension. Here's another example. If you were to make a sorting component, then it's from a software engineering and evolution perspective, you should give it a generic name that you can use on the inside. You can use bubble sort, but as an interface, you should have a generic name like sort, because then you can change bubble sort by quick sort, and be affected. Yeah, same for databases. And nowadays, of course, there are generic interfaces for databases. You don't need to invent them. But we don't want the interface to expose whether it's stored in a database or whether it's in a cloud. We just say store, and then the system figures out, and it allows you to change how you implement this storage functionality. This is an exercise I sometimes ask. I recommend that we don't do it together now, but it's quite interesting. So I ask students to make the design of a traffic light. And but the first question they need to answer for making the design is, what's the secret you want to hide? So you can think, what's the thing that you think might change, that you don't want to affect your interface. And I'll share the slides so you can read the answers later. And I hope that you enjoy the different ideas behind it. So then I want to go on to other generic design principles. We talked about divide and conquer, but there's a special one which is called separation of concerns. And again, these design principles they relate a bit to each other. It says that separate concerns should be handled in separate components. Of course, this links to having a single responsibility, but somehow things again evolve in fuzzy ways and in unstructured ways. But sometimes you need to reflect, okay, do I have functionality in my component that belongs together? Because otherwise I should split it up. And it also deals a bit with generality. And by the way, typical responsibilities, if you want to have categories in your mind, is either to know something or to do something, right? Your expertise as a component bit can be to coordinate, or your expertise can be to hold information. Here's an example that actually comes out of a telecom domain. These telecom and many other systems, by the way, they grow from a machine, and then machine becomes more electronic, and then it becomes more software. It's okay, and then they because it becomes software, it becomes smarter, and say, oh, yeah, we can somehow compress messages, and handling is about where in the network should we send the message, and okay, in this layer we can do some decoding, and then we handle it again, and we decode a bit more, and then we handle it again and decode. And this is just what the source code has come to look like. But I already highlighted with colors. There's actually two things going on in this source code: handling and decoding. So rather than having one component that does both, we should have two components: one that does handling, and a separate one which does the encoding and decoding. And this will give much clearer source code, which is better structured, easier to understand, and easier to maintain. So now the idea is that the solution at the bottom has applied separation of concerns. Yeah, I think we show this. Okay. Then I have added a few self-test questions as we're approaching the end of my my lecture. You can try, if you're able to answer these questions if they were given to you at an exam. I think question 1 and 2 are questions that I typically use in my exam. So Sathrio, you can borrow them. There's no problem. Yeah.
Thank you.
Producing an example of cohesion is actually good. I actually also like counter examples. It is actually difficult to come up with good counter examples. And then I move into my my summary. So we have discussed a number of design principles. What I would hope is that you now know them and that you can apply them. And I started by saying it's not so easy, because when I explain them, it makes a lot of sense and it sounds very logical. But the proof of the pudding is really in the eating. It's really when you make your own design and develop your own system that you start applying this. And I also think it starts by recognizing violations. You say, hey, I violated this principle here. I could do an improvement to what I've designed. So I just list the examples: information hiding, minimizing coupling, divide and conquer, separation of concern, and of course keep it simple. And this is also where the diagrams help out. As a final slide, I wanted to say something about research challenges in software architecture. And I have mentioned a few questions and some projects that have started exploring. But one question is, can we reason about the maintainability? We have lots of reasoning about complexity, and especially I'm interested in automating the reasoning about the architecture, right? So we we feed an architecture into the system, and maybe it's reverse engineered from the source code, but then the system recognizes, maybe the designer has implied he has used layering, and he's used information hiding, and he has used low coupling, and therefore this area of the system is well extensible, right? And this part is, hey, I can't see whether this data structure has been well say designed, because there's so many dependencies, and maybe I think this data structure is difficult to maintain. So I really think that that there's an opportunity to go there. And if you can do that, of course, you can move on to can I find possible improvements to the architecture, and this links a bit to one of the questions asked. So when do I need to actually change it? And it's sometimes called refactor. When I want to transition from my current architecture and change something new. And this can also be from the perspective of performance or security. Another question is, how do I check that the implementation actually conforms to my architecture, right? So imagine that you have a UML diagram or some other representation of your architecture as you would like it to be. But you know you're working with a team of 20 developers, and they work across 15 or more components, all of them programming and accidentally introducing dependencies and data structures. And so is there a way of checking that the dependencies that you get in the source code actually do not violate the dependencies that you plan for in your architecture? And there exists some approaches for this, but most of the time they assume that the design representation of your architecture is already close in terms of the same components as your implementation, but most often it's not. Actually, your architecture description will be at a higher level. We have some data on this, that if your implementation has like 100 classes, your design might have 10 or 20 classes, because you economize, right? You say, okay, I want to be pragmatic. I only represent the important parts, and that's perfectly fine. I think that's good engineering practice. But then you need to bridge this abstraction gap. Okay, I have these 10 classes in my design, and how do they map onto the 100 classes in my implementation, and which dependency is supposed to be where? And that's still an open question. And as I mentioned, I study the use of architecting, and I've tried to study what makes it effective. And I would say you have to have a good design from the start is important. But the other success factor is actually you need to continuously keep the architecture and your implementation in check. They need to match, because as soon what the typical pattern is, we make an architecture and then we start programming, and when we change the programming, and then the architecture no longer reflects the system, and then the architecture is useless, right? So it's only useful if you keep the architecture in sync with your evolving implementation. And again, there's opportunities for maybe you can automate this, but you still need to bridge the abstraction. So interesting challenges, I would say. And the bottom half of the screen, you see some screenshots that remind me of the project that we have done. So the first thing we've done, I've already mentioned, right? We've done a collecting of designs, and we used GitHub. So we have now 80,000 class diagrams of various type of designs, and we're trying to see if we can learn particular patterns, or we can see what's modeled or what's not modeled, or we can use it for, okay, does the implementation match the design? The second bullet is about trying to recognize patterns in software architecture. Of course, we need the data. That's why we have done the first step. But we have also built a machine learner that can automatically classify the responsibility of a class. We can feed this machine learner with either source codes, and then from the source code, it would extract features like I have so many methods, and I have so many getters and setters, and I have so much coupling. And then the machine learner has learned, okay, then you're probably a controller, or you're probably an information holder. And we use particular colors to represent these roles. And the picture that we have here actually has a red for information holder, and I think it has pink for structure and blue for service provider and yellow for interface. So you can start seeing patterns about, hey, how is the responsibility types of the classes in my design, and how is it across layers? And it's not accidentally that there's an interface at the top, right? Because it hides whatever is below it. And I think we can do much more in this direction. So this is this project in the direction of sense making. Can we make software that can make sense of software, right? It can tell us how software works. Yeah, and there's also various ideas on reconstructing and visualizing the relation between the architecture and the implementation. And on the right, you can see a little bit an attempt, but you can also see that this quickly becomes very complex. So at the top level, we have, I think, 30 or 40 components, but the amount of dependencies is already horrendous, right? And so again, we need a way of abstracting and coming up with better layouts. Better reverse engineering is still unsolved challenge. So with that, I would like to thank you very much for listening to my lecture. I'm happy to hang around for answering some questions.
Perhaps not a question, but a comment from me. I actually used the same example about traffic lights in my class last semester.
Okay.
And yeah, I think it's the exact same example. So, but those students are already graduated, so they're not in this class. So
Okay.
so this class haven't heard of that.
Yeah.
Okay, any questions from students? There is actually one question. Oh, for your information, we also stream this lecture on YouTube so that other students can listen to it who are not taking the class. And we have a question from another university actually.
Oh.
A student from another university, and I will be pasting it in the chat area. But unfortunately, I don't really understand the question. Maybe the English isn't quite good. So I think what he means is main problem.
Oh,
main problem. What is the main problem of implementation, software architecture, and quality?
Okay, I'm trying to think of it as well. What it could mean, this question.
What is the main problem of maybe implementing
software quality?
Software.
Well, there's a challenge in coming up with a plan and then making sure that the implementation actually follows the plan. That sounds simple, but it often is not.
Yeah. Yeah, I think it relates to your last slide here, how to check that architecture complies with the implementation.
Yeah. So the problem is actually that so there's a few things that make it difficult. The first, I suppose, is abstraction. Your architecture would be at a high level of abstraction. Maybe I should have maybe used a different example. But your design architecture, it has maybe 10 components. So one of the patterns that we found is that architecture pictures, they fit on one page, which is nice to know, right? But the implication of that is if your system becomes larger, your abstraction becomes bigger, because you still have the picture on one page, but now rather than representing 100 components, it represents 1,000 components. But it's so you get this distance between your conceptual picture and the implementation picture, and this is really not trivial. If you imagine this is a class diagram, it's simple, but this really represents components, like maybe from the lawnmower example, right, or for the radio alarm clock. And it's not always the case that there's this one-on-one mapping. You need to either manage it, or you need to reconstruct it in order to understand this mapping. Yeah.
Okay.
And then in practice, there might also be some heterogeneity in the implementation, right? So it's not always just one programming language. Sometimes it's multiple programming languages.
Exactly.
There's libraries for the user interface. And you need to recognize the technologies as well. So I've seen an example of, I think it was a student assignment for a travel agent. We don't do much traveling nowadays, but for the travel agent, at the logical level, it had a very nice class diagram, and in the implementation level, it was implemented as HTML pages and a database. Okay, it uses completely different concepts, even, right? The language for the implementation uses different concepts than the conceptual picture, and you really need to bridge an abstraction there. Yeah,
How do we bridge that?
yeah. We currently we don't know. Currently, we don't know. That makes it a good research challenge, I think. I think there's a few ideas for going in this direction. One is about recognizing technologies. So if you recognize SQL, you can infer that probably this is a database. If you recognize CCS, probably this is a user interface. If you recognize business processes, okay, I think this is a business process layer. But we can also use natural language a little bit. All right.
Mhm.
If you have a system and it deals with products and cards, you say, okay, maybe this is a web shop, right? And but we need to capitalize on domain knowledge. But I think we can do so much more, right? Because there is actually much more commonality in systems, both from a technological perspective and from an architecture and from a language perspective. Yeah. But it's not solved. But you can take an example. Just take your favorite open source project. I think we've started trying this for an email program. At the top level, you have okay, I have my contacts and I have my list of emails that I have sent. Okay, but if you look at the implementation, then you have okay, there's stuff about networks and there's stuff about encryption. And yeah, how does it map onto sending messages? You really need to look what's the aim of the technology rather than what does
Mm.
it implement, right?
Yeah.
So yeah,
Yeah. So part of the
but that's
difficulty is
really
because
advanced topic, I would say.
yeah, yeah. uh, One of the cause of the difficulty is because when architecting we should not be bound to a specific technology, but when implementing
Yeah,
we
yeah,
have
you have
differences
to.
in in
Yeah,
all kinds of technology. Okay,
yeah.
that was a good discussion. So maybe any other questions from the students?
Hello, sir.
Hello.
So it's me, Joel again.
Hi.
So just now we discussed about sometimes there's a difference between what we plan and what the implementation actually uses.
Uh-huh.
So but and this also correlates to to a few discussion I've been, that is when we use agile sometimes, because it is so focused on like sprint and this
Yeah,
kind of stuff, this short term development,
yeah,
then this kind of cycle makes it very hard to like focus on fixing, for example, technical debts, and
yeah,
also realigning
yeah,
the development
yeah,
effort to the architectural stuff.
yeah.
So, based on your experience when studying architecture and software, do you see any correlation that certain types of software development cycle leads to certain kinds of issues when we are trying to implement the architecture, and what the
Mm.
actual implementation is like?
Yeah, it's definitely the case that projects that use agile in the sense of okay, we have weekly cycles or something, and every week we deliver some working functionality. they have a short-term focus, and at some point when the system get large or there's more developers involved, you need to somehow also make time for the long-term plans. And there's two ways. One of them is actually, I think people like Fowler, who is one of the agile people, he also said, okay, if you work 5 days of a week in agile, one of those 5 days should be spent on refactoring, right? He said, okay, spend one of those days on improving the code, improving the structure. If that doesn't work, you can think about doing that on a once every 4 or 5 weeks basis, right? So we spend 4 weeks on developing functionality. We spend 1 week on cleaning up. Because if you don't clean up, your vegetable garden will become messy, right? This shown time and time again. This happens everywhere. And the fifth alternative, and this is what we've seen at Ericsson, is that because they are large organizations, okay, we have 4 teams working on developing features, and we have 1 team doing cleaning up. Yeah, and then it happens concurrently. So it's really a management priority, right? If you don't plan for it, it's not going to happen. So you must plan for it, and it's the same for documentation and architecture, by the way, right? If you don't plan for updating your architecture picture, it's not going to happen. But in Agile, it's easy to make it part of your definition of done, right? You said, okay, we develop a functionality. We just part of the definition of done is we test the new software and we update the documentation. Clear. Just assign a responsibility.
Okay, thank you, sir.
Yeah, I think uh, in recent years, people in the software industry have put great emphasis on refactoring, how important it is, and uh, the story about Ericsson was very interesting. I never know that there could be a specific team just to do cleaning up.
Yeah.
I'm really interested to know how it goes. Okay,
Yeah.
there was also a great discussion, and we have another question from YouTube. This time from our master's student. Does complicated software architecture always mean it's bad? Perhaps we should describe what is complicated first.
Well, my preference would be to give the short and simple answer, yes. Yeah. Yeah. So you can here on my slide, which is also a summary of the entire course. There's this bullet which says simplify, simplify, simplify. If you cannot explain your architecture as a simple picture, I would say there's something wrong. Again, if we can go back, I don't know where I had this example. This one. Yeah. And this is just a simple one. This is only a small system. If you cannot make a simple picture for a small system, what's going to happen if you're going to grow? But you're going to grow. You're going to get more features and more functionality and everything. You think that Mercedes-Benz 50 years ago knew that they were going to have so much software? No, they didn't know. But now they have 10 to 25 million lines of software driving around in a car. It's almost a data center on wheels, right? So
yeah. Okay. So, is there any other questions?
yeah.
So, a confession. I also work in the industry before I became a lecturer, and honestly, learning more about software architecture, I would be embarrassed to see my own old codes. But there's a story. During my time in the industry, I built border passage gate, so automating immigration process in the airport. So instead of having to deal with immigration officer, you can just scan your passport and your, something like that. I think it's a common thing now, but it, 10 years ago, it was not, especially in Indonesia. So I wrote the software for the system, and during our first iteration of the product, we didn't have a clean architecture, and it was so messy, and it took 2 years to complete the first version. And when we were going to release another version for the second version, we do it all over from scratch with a clean architecture. And software wise, it only took me and the team 2 days to complete the system, to write the code that works well. So yeah, that's how important a clean architecture is.
Yeah, I
from
think
my
so.
own first-hand experience.
Yeah, I think so as well. So I'm going to stop sharing my screen, I think. Can I do this?
Sure. Okay, students,
Yeah.
do you still have any more questions? We already passed our time, but I think we can still do it some more discussions. Okay, what do you think of software service-oriented architecture in creating a community for applications?
Okay, I think you can do that. That's perfectly fine, but it doesn't matter so much what technology you use, right? You can make a good application in many technologies, and recently there's some tools that have emerged around low code. Maybe you can look into that. There's let me think. There's a tool called Mendix. There's a tool called OutSystems. So I'm typing it into the chat. And they actually allow the very efficient development of applications, and they exploit the fact that the architecture of those systems is standardized, and that there's lots of frameworks that we can use. So you just design the user interface, you design the data structure, and you design the business process, and then you press go, which used to be compile, and it compiles it for you, but it puts the storage in the cloud, it deploys it on the telephone, you can download it from the App Store. The benefit is that it integrates the frameworks and it integrates the development tool chain to a very high degree. But moreover, it only asks you to do very little, because it's just filling in all the gaps in the standard architecture. So it's interesting technology to have a look at, I would say. I don't have any stocks in these companies, by the way. I do talk with them, but I don't own them.
Flow code. Okay, so you guys can read about that in depth later after this session. I think I will look into that too and see if I can integrate it to our other courses maybe.
Yeah. Actually,
Okay.
I don't have a lecture on it yet, so I have to update my lectures and integrate this topic because I think it's really important.
Yeah, it's also very new, I think.
Yeah, it is very new. Yeah, but even then, you almost don't need to worry about SOA and WSDL, because everything happens under the motor. Was it under the hood of the engine of the application generator? Yeah.
Okay, I think our time is up. That's so unfortunate, but that's how things go. So thank you very much, Professor Michel Chaudron, for
my pleasure.
Giving a guest lecture. I hope this can be a start of longer term.
Yeah, Exactly. So I
Operation.
hear people in ITB would like to collaborate a bit more with our university. So
Mhm.
I'm looking forward to having more conversations also with the staff. And if there's something that is specifically of my interest, is to see if we can find one, maybe two PhD students that are from ITB that we can maybe co-supervise together from Eindhoven.
Sure. That will be great. Okay. Students, maybe you want to say something to our guest professor, or not? Maybe. Well, earlier we have already greet our guest professor with our cameras on, and maybe it's another perfect send off to turn on your cameras once again and say goodbye for now to our guest professor. Okay. Say something, please, students. Thank you for the lecture, they said in the chat room.
Yeah, I see it. Thanks, everyone. I hope it was a bit insightful.
It is. Okay. Well, that was all for now. I think we can hope to see each other again soon in other opportunities. Thank you very much.
Yeah, same here. Thanks, everyone. Bye-bye.
Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Hello.